Okay, we've seen that if you apply a constant force to an object through a given displacement parallel to the line of the force, that you have a constant change. That you can predict the change in the kinetic energy of the object. Okay, so that is F net delta x equals a change in kinetic energy. Recall, we got that by taking the equation Vf squared equals Vi squared plus 2a delta x. And substituting A equals F net over M. Rearranged, and we get this result, and you should understand that derivation, that reason. Now, there's another situation where we want to think about what happens if you exert a net force for a certain time interval. Okay, so we want to see if there's some significance. Obviously, if we look at F net delta t, this is also going to have an effect on the motion, which is proportional to delta t, as opposed to the effect here that's proportional to delta x. Now that's not going to change. I mean, this will change the kinetic energy, but that's not the thing that is directly the result of an F net delta t. It's what we call change in momentum. So I'm going to say this. And we generally use P for the momentum. It's fairly common symbol to use. We don't want to use M for momentum because mass has already got M. Okay, so maybe we go to the next letter of the alphabet, P. I'm not sure there's another connection, and I'm not sure that is the connection between why we use P for momentum. Anyhow, okay, this comes about very easily, even more easily than this one does, because we know that Vf equals Vi plus A delta t. Okay? Now this is for constant force. So I'm not going to even specify that. So maybe here, constant F net implies that the acceleration equals F over m. So if m is constant as well, from this relationship, we immediately get, well, plugging this in, we immediately get something that we can put into the form F net delta t equals mvf minus mvi. Of course, for homework, I'll ask you to do that rearrangement. It's very simple, much simpler than this one, and this one's simple enough. Okay, so we call F net delta t is the impulse. The force F net
We are.
for time interval delta t P, which is mv, we're going to call momentum. So F net delta T equals delta P. Impulse equals change in momentum. And that's the change in the quantity mv or P, not written very well, which is change in momentum. Now this has straightforward consequences. For example, we apply a net force of 500 newtons, which is not a huge force. It's a force that an ordinary male pretty easily bench press, so it'd be a weight you could pretty easily bench press, more or less easily, and very easily if you're training. The net force of 500 newtons. Let's apply that net force. Two seconds to a mass of 10 kilograms. Okay, how does that fit into this scheme? Well, we know F net, we know delta T, and we know the mass. So, I'm not going to write an equation, let's just look at the individual quantities. F net delta T is what? It's 500 newtons. Times 2 seconds. It's going to be 1,000 newtons a kilogram meter per second squared. It's going to be 1,000 kilogram meters per second. Now, delta P is mvf minus mvi, which equals, in this case then, m is a 10 kilogram mass, and I'm actually going to then write that as 10 kilograms times delta P. Well, F net equals, impulse F net delta T equals delta P. Impulse equals change in momentum. So our 1,000 kilogram meters per second equals 10 kilograms times delta V. And delta V then, very obviously, equals 100 meters per second. So applying this impulse, a 2-second, 500 Newton impulse, so we push with a pretty good force and maintain that for 2 seconds, which is a little harder than bench pressing 500 Newton weight. But you know, a decent football player can do it, decent lineman, and so can a lot of other people. But, so it's a pretty good effort though for 2 seconds. It's not going to exhaust you. If you can maintain the force, you could accelerate a 10 kilogram object in such a way that its velocity changes by 100 meters per second. Now, you couldn't actually do that. If I give you a 10 kilogram object and tell you to apply a force of 500 newtons for 2 seconds, you can't do it, simply because that thing is going to be moving faster than you can, or faster than you can move any part of your body within just a fraction of a second, okay? So if you have some kind of leverage, light lever that you can, light beam that you can exert 500 newtons on for 2 seconds, and the other end of the beam propels this object, theoretically you could do that if you eliminate friction and the beam was light enough. Okay, you can get close to 100 meters per second. Anyhow, that's not the point. There are a couple of important physical points there, but the main idea is simply that this situation, even though that's a force you couldn't personally exert on a 10 kilogram mass, if something did exert that 500 Newton force on a 10 kilogram mass, it would accelerate it by 100 meters per second. Okay? And so you could think maybe a rocket engine on a 10 kilogram mass. Of course, the problem with a rocket is you're burning fuel. As you burn fuel, the mass decreases. Well, that's a little more complicated situation. But you get the idea. Okay. Now, let's consider another situation. We've got an unknown net force acts at a mass of 300 kilograms. Slowing it from 20 meters per second to 15 meters per second in half a second. What's the, I'll put it in parentheses, time averaged net force. If you average the net force over time, then, well, I'm just going to assert this, although a little bit of calculus makes it real clear, and we'll talk about that. Let's just get the general idea down. Okay, for time average net force, F net bar, when a time interval delta t, where the time average is taken over the delta t, and we'll be more specific about that. Okay, when a time interval delta t, in any case, well, the impulse is F net bar delta t. Now, the impulse of the net force is always equal to the change in momentum. Again, we prove that using a little bit of calculus. Okay, so F net bar delta T equals delta P. And F net bar equals delta P over delta T. In this case, delta P is MVF divided by MVI, and you can figure that out as easily as I can, so I'm not going to write out the details, but MVF is 300 kilograms times 15 meters per second, and MVI is 300 kilograms times the initial velocity, 20 meters per second. Okay, so MVF is then 4,500 kilogram meters per second. MVI is 6,000 kilogram meters per second. So I'm not going to write out all the details of that calculation. I've got the 6,000 wrong place. There it is. There's your change in momentum, which is negative 1,500 meters per second. You got to divide that by 1/2 second, which is going to then multiply that 1,500 meters per second by 2 and give you another second in the denominator, and you end up with 3,000 kilogram meters per second squared, which is, of course, 3,000 newtons. Now that's the average, time average of the net force, meaning if you were to draw F net versus T for a time interval of 2 seconds, between whatever starting value of T you happen to be using with your clock, you happen to measure maybe with respect to the clock, and that's not 2 seconds, it's 1/2 second. Okay, so again, the time interval of 1/2 second between whatever time occurs when the force is first applied and the time when it's removed. Your net force, which can be visualized as the force corresponding to some curve between these two times, has an integral, because of course definition of an average value of a quantity with respect to whatever the other quantity is. Now, the average value of F net averaged over time is the integral of F net dt over delta t. I'm being a little careless with the notation, but an intuitive idea that I believe I asked you to think about and review last time we met. Because it's a basic fundamental idea of calculus that people never seem to understand when they come out of a calculus course. Anyhow, you have this. So the integral, of course, is represented just by the area under the curve. And the average force is the constant force that would be exerted on that interval to give you the same area. Okay, well, I'm thinking that, well, let's see, maybe this constant force got a question mark here. Could this be your FNAP? Well, to see whether that's a reasonable FNAP, we can shade the regions above the curve, the straight line, and we can then shade the region below the straight line. And if the area, total area of the regions above the straight line is equal to the total area of the region or regions below the straight line, then the straight line is a pretty good representation of FNAP. Now, in this case, I think we've got a little more area up here. I think the area here is maybe equal to the lesser of these two, the area in the lesser of these two humps. So I probably should have put the line a little bit higher to reduce the area above the curve and increase the area below the curve. I wouldn't have had to move it very far. But I've got a reasonable estimate of FNAP here. And if I have a scale on this graph, then I can estimate my FNAP. If I know what the function is for FNAP, I can integrate it on the interval and divide by the length of the interval and find the average FNAP, which allows me to find the impulse. Okay? Well, from this whole argument, we can say that it follows that F net bar delta t is the integral of F net dt divided by delta t, giving the average F net multiplied by delta t. And that's just the integral of F net dt. Now, to be rigorous about that, I have to specify the interval of integration. That's fairly easy to see. And your book, of course, will explain that to you just fine. Okay? So right here is actually your definition of impulse. Okay? Okay, impulse is integral F net t over delta t, and to write it out a little more. Explicitly, this, the integral going from t1 to t2, the time interval being, of course, t2 minus t1. Must have been looking at 2 when I wrote that. Okay, so there it is. Here are a couple of applications. We'll take a quick look at one more.